So I'm going to call this axis y and that x. And we already have some definitions for the angles themselves, right? If I have a little theta, don't draw this yet. I'm just going to say if this is theta, I need to add a direction on it. But we already said that sine is a certain value, the cosine is a certain value, and the tan, if I relate it within a triangle. Does anybody remember what those values are? Anybody? What was sine?
Opposite over hypotenuse.
Yep, so what would be opposite in here? If I said this was a point x, y, let's say.
The little dotted one.
Yep. That would be the x or the y? The y, yep, it's the y coverage. And the hypotenuse, let's say I have an r here, that's going to be y over r. So cosine is then x over r, and tan is y over r, right? But the setting in the unit circle is for the radius to be equal to 1. So that means all of that translates to the cosine of theta being equal to x, and the sine of theta being equal to the y-coordinate of any point, right? Because it's y over 1 and x over 1. And the tan doesn't really change, it's still y over x. So you don't need these. All I wanted to get at is that cos of theta is x and your sine of theta is y. So any point from now on, when you think of a point on the circle, can be described by cos theta as the x-coordinate and sine theta as the y-coordinate. Okay, now that is on the unit circle. There's some scaling happening on different radii, right? If I increase the radius there, some things will change. But as it is, you can always use the x-coordinate as your cos and your y-coordinate as your sine. So we'll go back to those special values. And for each point here, we're going to start with the first quadrant. And what would I say for this angle, if you remember the special angles we talked about last class? The smallest one, well, the smallest one technically is 0. I'm going to skip that for now. It would be 30, that's right. So I'll say that this here is 30 degrees. And I'll create the little triangle. We know this is 90. And what were the values for cosine and sine of 30? If you don't remember, we said the smallest side is 1, so in your triangle, the smallest side is 1 if this is 60, and that's 30. This goes to a 2, and this is root 3. Okay, so cosine of 30 would be what? Adjacent over the hypotenuse, which is 2. What about the sine? Sine would be opposite, so that would be 1 over 2, yeah? Okay, so that describes now the point when the angle of the terminal arm with the x-axis is 30. Are we convinced of that, or should we check one more way? Okay, let's do a quick check. So if you remember, before we had our special value of root 3 over 2. So if I say somewhere here, cos of 30 is known to be root 3 over 2 from our special triangle. In this particular triangle, using my identity, whatever values I have, if this was y and this was x, and this was given as 1, I would just get my adjacent, which is x, over 1. So I'm just making up a little equation. So if cos of 30 is the same as cos of 30, then root 3 over 2 is equal to x over 1. So that gives me the x of root 3 over 2. So that's the algebraic way. Really doesn't matter how you think of it. So you either remember the pattern, cosine being corresponding to the x, or the actual algebraic solution. Okay, so now if I go for sine for that same angle, what did we remember it to be from before? As a value in those special triangles at the top? 1 over 2, that's right. Okay, and then sine of 30 in this particular triangle as an expression is the opposite side y over 1. So once again, I set up my y over 2 is equal to y over 1, and if I solve for y, I get 1 over 2. Okay, so this is from your special angle, and this here is just from the unit circle triangle. Okay, so that's one way, but like I said, just reiterating one more time, if you take any point here, we knew before that cosine is just x over r. The r is 1, so the cosine of theta always collapses to this value here. You can just remember that the x corresponds to cosine, and the sine corresponds to y. It's not a shortcut of any way. I mean, you have the derivation here if you need to, but you don't have to do this every time, okay? Just remind yourselves that cos is x and sine is y. So now if we go to the next triangle, let's say pink, what would be the value of the theta here? What angle am I looking at from the special set that we discussed? 30, another 45, that's right. So I have 45. And then we're going to discuss 60. Okay, so let's say for the 45, what is cosine and what is sine? That's one of the easier ones, right? The 45, because what do you remember about the cosine and the sine? We said the smallest side is 1, right? So I have that triangle at the top. And then what is the hypotenuse? If the two sides are 1 and 1. We have root 2, right? So cosine and sine of 45 are equal to each other, and they're just 1 over root 2. Or rationalize, we go with root 2 over 2. And we said they're equal. Are we convinced they're equal? The sine and the cosine? Okay, so if you take your 45 here, because you have the isosceles triangle. Okay, and finally, we have for 60. Now you can do this two ways. You can go back to your triangle, the special one, with one side root 3, 1, 1, and the hypotenuse 2, and use the sides there to find sine and cosine. Or you remind yourself that it's the same triangle that we used in the first case here for 30. But what will happen to the coordinates once I'm at this point? Sorry? Yep, they do. The x and y switch. You can think of it that way. And that's not incorrect to say because... So remember, cosine of 30 is sine of 60, and sine of 30 is cos of 60, right? But it all comes from this triangle here. But it was correct to say that the coordinates flip because if we remember transformations, you don't have to write this down. But if you extend this line here at 45 degrees, this is your y is equal to x line, right? So I'm reflecting this point into that line, so it makes sense that the two coordinates switch up, right? Does that make sense? Okay. And then we can keep going, and we're going to keep using transformations and bringing back that knowledge that was so solid. We finally did it, right? Okay, but you don't have to draw this y is equal to x line. That was just a little note. Okay, so now we go to reflecting it into the y-axis. So I'm going to go to this point. Okay, so what angle would that correspond to? So the first one was 60. If I look at the 180 minus 60, that's right. That would be 120. Does it look like a 120? Not really, but... Okay, so that's 120, and the coordinates that correspond to that, because I'm reflecting into the y-axis, what will happen to 1/2 and root 3 over 2? I'm going to say here reflect into the y-axis. The coordinates, so these points are on the same y line, right? So what will happen to the y coordinate? Does it change or stay the same? It stays the same, so root 3 over 2. I'm not going to use this line. And then what happens to the x coordinate if I'm on the other side of the... It's a negative value. Yep, so we have a negative 1 over 2. So now I'm going to keep going. The next one, use the same color. So we have 145. Okay, I'm going to change my diagram just a little. So this is 120, more exaggerated. And 145 will be narrower. This here is 145. Okay, and the coordinate here, again, the y will stay the same. I'm on the same line as the other playing point. And what about the x? I'm still reflecting into the x-axis and y-axis, so also negative. Root 2 over 2. Okay, so all of these are coordinates, so I can keep going. And the last one, you guys can finish this. Okay, and the angle here would be what? 130 minus 30 is 150. Yeah, it is 135. Otherwise, we get a sum of 190. Okay, so now we're going to keep going into quadrant 3. So this was quadrant 2, and this was 1. And what am I reflecting into now if I go onto the other side? Quadrant 3. Okay, we're reflecting into the x. Okay, so I'm going to say reflect into the x-axis. Okay. So now, as I move downwards, the x-coordinate stays the same this time. So I'm going to fix the negative root 3 over 2. But if I'm reflecting into the x-axis, what coordinate changes? The y goes to a negative. Okay, so we have negative 1 over 2. And just for fun, I guess, this whole angle here is 180 plus 30, which gives us 210. Yep. And keep going. We have one more pink one. And this one goes to negative root 2 over 2. The x is the same. It's on the vertical line of the other pink point. And we have negative root 2 over 2. And the angle, a little messy, but doable. So 180 plus 45 gives me 225. And the last one that we're going to do here, you can finish the fourth one for homework, but This one is 100 and what? No, 200 and what? 270 minus, isn't it 250? Yeah. So it's 270 minus this was 60. This is, oops. Let's say 250. We'll double check the algebra in a bit. Is it 240? No. You can double check in a sec. Okay, so now we're just going to double check the negative 1 over 2, negative root 3 over 2. So again, reflection about the y is equal to x line, if you check that again. And all this means is you can take these coordinates as they are and use them for sine, cosine, and tan of these values, right? So all you have to remind yourself, so if we take, let's say, sine of 225, all I have to do on a test is first determine the little beta that we talked about before. So this would be, let's say, your beta angle for 225, right? You know it's quadrant 3. And you know you're using a beta of 45. Okay, and if you go and you select that point, sine of 25 would be your y-coordinate, so negative 1 over 2. If I were to ask you for cos of 225, use the same reasoning as above, so the same quadrant 3, I know beta is 45, so I'm going to go with negative root 3 over 2. So these you might remember quickly, the angles between 0 and 360 degrees, because that's one full rotation through the circle, right? And this also matches up with, you all remember our cast, right? So all the signs should work out to all the rules we talked about before. Okay? The sine, cosine, and tan being positive in those quadrants there. But the reason why this is really useful is, for example, if you monitor weather or temperature and you try to see if there are certain models that are maybe going away from the norm, you would, let's say, simulate a sine curve, and you would actually look at time as measured in degrees. We'll do a bit of a conversion later. But as you flow through time, there's a circularity that you expect, right? Repetition of patterns. So if I go around the circle a couple of times, I should still be able to figure out the sine and cosine. Okay? So the sine of 225 will be the same if I were to fully rotate. So I have, let's say, sine of 225 plus 360. That should be the same. And that's why the circle is so useful. Okay? You don't have to recalculate each time, just remember the pattern. So cos of 225, I'll also say minus. So it doesn't matter what direction you go in, the ratio should stay the same, which is, root 3 over 2. So you can cover any amount of angles this way. And it's not always special angles, right? It can also be other values. Isn't this the most elegant thing you've ever seen? Right. Okay, so we'll leave it for now. We'll see what we can do in a bit once we start the other handout. But for now, let's see what happens when we don't have special angles. Well, you already know this because it's mostly calculator work. But if you're given a ratio in decimal form, how would I figure out the actual angle? Inverse, okay. Now, what will that give you if you punch it into your calculator? Well, it gives you one value. What is it? Sorry? Casper has the calculator? Okay. What is it? Theta. Okay, 0.62. Okay. Okay, so we have 1. That puts us in quadrant 1, right? And you'll always get answers that will usually be in quadrant 1, but we also know we have one more angle because the sign is also positive where?
Quadrant 4.
Quadrant, what? The sign.
Oh, what's that?
What quadrants do we have sign positive in?
Quadrant 2.
1 and 2. But I wrote down the cast there for a reason. So that means A and S are positive, so I can be in quadrant 1 or quadrant 2. March break was too long. Okay, so then we have these two angles. So we're going to treat the first one that we found as our little beta, right? So beta is always orange. So I'll write in brackets, this is my beta, 13.62. So that gives me another answer for quadrant 2, the theta 2, as 180 minus this 13.62. So I get one more answer there, which is what? 3.8, let's say, based on our rounding here, but you can use whatever you want. Not that picky with these values. Okay, so one thing you have to remember is that you will have two solutions for most of these. The first answer you get will usually be the beta, or quadrant 1, and then you have to remember your cast. Okay, so technically here will be theta 1 and theta 2, and as a final answer, you normally write, but again, not too picky, 13.62 and 157.38, just as a list, as a final declaration that you know there are two values there.
57?
157, isn't it?
167.
Oh, is it? I thought you said 6.
I said.
You're just testing me, that's okay. Okay, so 1, and then you guys try the next one, but I will do it in parallel with you. So remember, first I'm going to consider the positive, so that will probably give me a quadrant 1, but what will the other solution be in? The fourth, that's right. This time it is 4. 25 plus 360. That should be the same. And that's why the circle is so useful. Okay? You don't have to recalculate each time, just remember the pattern. So cos of 225, I'll also say minus. So it doesn't matter what direction you go in, the ratio should stay the same, which is root 3 over 2. So you can cover any amount of angles this way. And it's not always special angles, right? It can also be other values. Isn't this the most elegant thing you've ever seen? Right. Okay. So we'll leave it for now. We'll see what we can do in a bit once we start the other handout. But for now, let's see what happens when we don't have special angles. Well, you already know this because it's mostly calculator work. But if you're given a ratio in decimal form, how would I figure out the actual angle? Inverse, okay. Now, what will that give you if you punch it into your calculator? Well, it gives you one value. What is it? Sorry? Casper has the calculator? Okay. What is it? Theta. Okay, 0.62. Okay. Okay, so we have 1. That puts us in quadrant 1, right? And you'll always get answers that will usually be in quadrant 1, but we also know we have one more angle because the sign is also positive where?
Quadrant 4.
Quadrant, what? The sign.
Oh, what's that?
What quadrants do we have sign positive in? 1 and 2. But I wrote down the cast there for a reason. So that means A and S are positive, so I can be in quadrant 1 or quadrant 2. March break was too long. Okay, so then we have these two angles. So we're going to treat the first one that we found as our little beta, right? So beta is always orange. So I'll write in brackets, this is my beta, 13.62. So that gives me another answer for quadrant 2, the theta 2, as 180 minus this 13.62. So I get one more answer there, which is what? 3.8, let's say, based on our rounding here, but you can use whatever you want. Not that picky with these values. Okay, so one thing you have to remember is that you will have two solutions for most of these. The first answer you get will usually be the beta, or quadrant 1, and then you have to remember your cast. Okay, so technically here will be theta 1 and theta 2, and as a final answer, you normally write, but again, not too picky, 13.62 and 157.38, just as a list, as a final declaration that you know there are two values there.
57?
157, isn't it?
167.
Oh, is it? I thought you said 6.
I said.
You're just testing me, that's okay. Okay, so 1, and then you guys try the next one, but I will do it in parallel with you. So remember, first I'm going to consider the positive, so that will probably give me a quadrant 1, but what will the other solution be in? The fourth, that's right. This time it is 4. We usually use Roman numerals. I did say this right before, or not? If I didn't, it's Roman numerals for the quadrants. So what do we get for the first value, or the beta? Say that again?
83.36.
Okay, 36 degrees, right?
Yes.
Okay, and so that automatically gives me that beta. And so theta 2, how do I find theta 2 if I'm in quadrant 4? Okay, 360 minus that, that's right. So I have beta is equal to theta 1 here, and the second angle, you get your 360 degrees minus 83.36. And that gives us what? 276.64. Okay, so you guys can keep going with the other one. Oh, final declaration, but again, not terribly important. Yep. Oh, yeah, that's right. What? Why might that be? It's flawed. This is the old one.
Because it's 5.4335.
Yeah. That's right. Well, no, in general, the sign, Henry, the sign, sine and cosine, will be stuck between values of 1 and negative 1, okay? And well, you can look at it as either using this triangle here, for example, right? Whatever sign I have, I'm always going to look over the hypotenuse, right? Sine or cosine. Does everybody agree? So as a rule, because I'm going over the hypotenuse, I'm always going over the larger side. So whatever value one of the other sides has will give me a less than 1 ratio, okay? So if you look at any number smaller than 2 over 2, you'll always get this as less than 1. Okay? So it will always be stuck between 1 and negative 1. Or if you use the unit circle, you know the radius is set up as 1. So these ratios, the coordinates themselves, will never go above 1 or below negative 1, because this point here is negative 1, 0. this is 1, 0. That at the top is 0, 1. And at the bottom I have 1, 0, negative 1. Okay, so your points will always be stuck between those values. And actually, this discussion brings up the issue of sine of 0, 180, 360, etc. So for all of those that are multiples of 180, right, 0, 360, 720, all of those, you'll have sine equal to 0, and the cosine will either be plus or minus 1. If you're on the y-axis, you'll have cosine 0 and sine being 1 or negative 1. And the last one here, we said no solution, because the sine of theta will always be between 1 and negative 1, and the same for cosine. Whoa, that's a lot of homework. We'll select some of it. Sorry? Okay, so I'll just use this grid here for this 0 business. So if I have an angle of 0 degrees, then I'm using this point here of coordinates 1, 0. So that means the sine of 0 and the cosine of 0. I'm just using my coordinates. Oops. That should be 0. So sine of 0 is 0, cosine of 0 is 1. If I switch to the other side at 180, the sine will remain the same because that's the y coordinate of the point, but the cosine of 180 goes to negative 1. Oh, that should say 180. Okay, and so this is one arm, the 0 degrees. You can't usually drive, but we'll still say theta is 0 for that. And the second arm here, let's say theta is equal to 90, and we'll do that in a bit. And the third arm, if I look at this, theta is equal to 180. And for this, we use point 0, negative 1, 0. Are people falling asleep?
No.
Okay, and so one more, well, two more. Let's say theta is equal to 270. We're looking at the bottom here, so this would be theta is 270. And I'm using point 0, negative 1. So sine of 270 and cos of 270. So the sine, we said, is the y-coordinate. That's negative 1. The cosine is 0. And you guys can do the 90, sine of 90, and cosine of 90. Cosine stays at 0 because I'm on the same x-coordinate, and sine of 90 is 1. Exciting stuff, right? Okay, so we can go to our next handout and do a bit of practice. I think